Hello, and welcome to the first video for section 11.1, which deals with sequences. The main techniques necessary for this section are the ability to take infinite limits and the ability to manipulate inequalities. We begin with a definition. A sequence is a list of real numbers written in a definite order, usually indexed by the natural numbers, A1, A2, A3, etc. An is called the nth term. For the list A1, A2, A3, we usually use the shorthand an, n equals 1 to infinity. Or if we are not concerned with the index, sometimes we simply write an. Example 1. Let's take the sequence n divided by n plus 1 from n equals 1 to infinity. It has as its nth term an equal to n divided by n plus 1. The first few terms of the sequence are 1/2, 2/3, 3/4, 4/5, etc. Let's look at another example. Find a formula for the general term an of the sequence 3/5, -4/25, 5 divided by 125, -6 divided by 625, 7 divided by 3125, etc. Note that this is just an exercise in pattern recognition. Note that A1 equals 3/5, A2 equals -4/25, A3 equals 5 divided by 125, and so forth. And observe that the numerators increase by 1 when going to the next term. The denominators are all powers of 5, and the signs alternate between positive and negative. Thus the nth term is an equals -1 to the n minus 1 times n plus 2 divided by 5 to the n. It is worth noting at this point that sequences are simply lists of real numbers, and thus not all sequences have simple defining equations like the last two examples. Now let us think about the sequence n divided by n plus 1 some more. The first few terms of the sequence are 1/2, 2/3, 3/4, 4/5, etc. Notice as we go further and further out in the sequence, the terms of the sequence are getting closer and closer to 1. For example, A10 equals 10 divided by 11, which is approximately 0.909. And A100 equals 100 divided by 101, which is approximately 0.99. We make this behavior precise. We say that the sequence an has limit L if for every epsilon greater than 0, there is a corresponding integer capital N, such that if n is bigger than capital N, then the absolute value of a sub n minus L is less than epsilon. We use the notation that the limit as n goes to infinity of an equals L. Or we might write an goes to L as n goes to infinity. Let's think about what this is really saying. Intuitively, a sequence has the limit L if one can make the terms of the sequence arbitrarily close to L by going out far enough in the sequence. A simple way to illustrate this is by thinking of the terms of the sequence plotted in the Cartesian plane. So we plot the points n, a sub n. Notice that for any positive epsilon range from our limit L, we can go out far enough in the sequence so that eventually all of the terms of the sequence cluster within this range. If we plot the sequence n divided by n plus 1, then we see that as we go further out in the sequence, the terms get closer and closer to 1. Therefore, the limit as n goes to infinity of n divided by n plus 1 equals 1. Keep in mind that a sequence need not have a limit. Here is a simple sequence that has no limits. We just take the integers 1, 2, 3 and repeat them. The sequence has no limit because no matter how far you go out in the sequence, the terms never get arbitrarily close to any real number. Thus we say a sequence an converges if the limit as n goes to infinity of an exists. Otherwise, we say that the sequence diverges. The notion of the limit of a sequence should not feel like a new concept, as you have already dealt with a similar concept when dealing with infinite limits of functions. Compare and contrast the definitions. Notice that the only difference between the definitions is that for sequences, n is required to be an integer. Thus, unsurprisingly, we have the following theorem. If the limit as x goes to infinity of f of x equals L, and f of n equals an, where n is an integer, then the limit as n goes to infinity of an equals L. This theorem simply says that if the points of the sequence lie on the graph of a function, then the limit of the sequence is the same as the infinite limit of the corresponding function. The moral of all of this is that whenever a sequence has an explicit formula, then we can understand limits of sequences as limits of familiar functions. Example 3. Recall that we claim that the limit as n goes to infinity of n divided by n plus 1 equals 1. The corresponding function to the sequence n divided by n plus 1 is f of x equals x divided by x plus 1. As the limit as x goes to infinity of x divided by x plus 1 equals 1, it follows that the limit as n goes to infinity of n divided by n plus 1 equals 1. As you would expect, all of the limit laws from before hold for sequences, so keep them in mind when computing limits. Similarly, we also have the notions of infinite limits of sequences. We say that the limit as n goes to infinity of a sub n equals infinity if for every positive m there is a positive integer capital N, such that if n is bigger than capital N, then a sub n is bigger than m. This essentially says that by going out far enough in the sequence, you can make the terms a sub n as large as you want. For example, the limit as n goes to infinity of the natural log of n equals infinity. This is because the limit as x goes to infinity of the natural log of x equals infinity. As we saw before with infinite limits, we can also go to negative infinity, and the definition is similar to the one above. Lastly, don't forget the squeeze theorem or the sandwich theorem, which also applies to sequences. The squeeze theorem says, suppose that xn, yn, and zn are sequences with the property that for n bigger than or equal to capital N, xn is less than or equal to zn is less than or equal to yn. Furthermore, suppose that the limit as n goes to infinity of xn equals the limit as n goes to infinity of yn, which equals L. Then the limit as n goes to infinity of zn equals L. The following figure illustrates the theorem. Notice that after capital N equal to 11, the orange sequence is sandwiched by the blue and red sequences. Let's do a final example. Compute the limit as n goes to infinity of 1 over n squared plus sine of n divided by n. Note that the limit as n goes to infinity of 1 over n squared equals 0, as the limit as x goes to infinity of 1 over x squared equals 0. Now since negative 1 is less than or equal to sine of n is less than or equal to 1, we have that negative 1 over n is less than or equal to sine of n over n, which is less than or equal to 1 over n. Since the limit as n goes to infinity of 1 over n equals the limit as n goes to infinity of negative 1 over n, which equals 0, it follows by the squeeze theorem that the limit as n goes to infinity of sine of n over n equals 0. Therefore, the limit as n goes to infinity of 1 over n squared plus sine of n over n equals the limit as n goes to infinity of 1 over n squared plus the limit as n goes to infinity of sine of n over n, which equals 0.